Welcome back. Well, I've been requested to do several problems by our friend Akash, so I thought I would keep doing them. I'm skipping around a little bit because I think if I did all of them, it would just generate, too many videos. But I encourage all of y'all to let me know if you feel that there's something that I might have missed. But anyway, I'm just going through some of the problems he gave. So this one, and I actually almost find it funny because they use such formal language for something that's actually a pretty intuitive concept. Well, they say use the monotonicity theorem to find where the given function is increasing and when it is decreasing. Monotonicity. Monotonicity. Monotonicity function. Theorem. Makes it sound very serious. Well, all the monotonicity theorem, at least if I'm remembering things properly, all it says is when the derivative is positive, when f prime of x is greater than 0, your function is increasing. And when the derivative is negative, your function is decreasing. And why am I kind of, disparaging of this? Well, it's, what's the derivative? The derivative is the slope. And you learned in Algebra 1 that if the slope is positive, the graph of the line is increasing. And if the slope is negative, the graph of the line is decreasing. And the only thing that's different now is that, this function isn't necessarily a line, it's a function, so it could be a curve. But having a positive slope means that the value of the function is increasing. For every change in x, there's a positive change in y. And similarly, a negative slope says that for every change in x, no matter how small, there's a negative change in y. So there's nothing fancy here, but let's see, they gave some examples. So they want us to use this theorem to find where the given function is increasing when it is decreasing. So the first function they give is f of x is equal to 3x plus 3. Well, what's the derivative of this? F prime of x is equal to 3. Well, for any value of x, this is positive, right? F prime of x is positive for all values of x. So this thing, using the monotonicity theorem, is is increasing for all values of x. And you could have done that in the 9th grade. How? Well, you would have said, well, this is the slope y-intercept. The slope is 3, so this is an increasing function. The function will look something like this. The y-intercept is 3, and its slope is 3, so this function looks something like that. And so it's increasing over from, you could say from minus infinity to positive infinity over that interval, if you wanted to be fancy. But this is really just a lot of fancy terminology to talk about, I think, something fairly straightforward. Anyway, the next one looks a little bit more interesting. h of z is equal to z to the 4th over 4 minus, and I hope I'm reading this right, 4z to the 3rd over 6. So let's see if we can figure out when this is increasing and when this is decreasing, when the function is increasing or decreasing. So what's the derivative of this? H prime of z is equal to, let's see, 4. Well, this will cancel out, so it's z to the 3rd, right? 4 is z to the 3rd over 4, so it's z to the 3rd, minus, let's see, 3 times 4 is 12z squared, but 12z squared over 6, so it's 2z squared. And so we just have to figure out when is this function greater than 0 and when is this function less than 0. And to figure this out, we really just have to break out our algebra toolkit to figure out, well, when does this function equal 0? So let's set z cubed minus 2z squared is equal to 0. And we could factor, we could factor out a z squared. And then we have z minus 2 is equal to 0. So we know that either z squared is equal to 0 or z minus 2 is equal to 0. So the points at which the derivative is 0, so h prime of 0 is equal to 0 and h prime of 2. And that's just our algebra 2. So h prime of 2 is equal to 0. And so we just have to figure out what happens in the interval, maybe when we're below 0, between 0 and 2, and then above 2. So what is the derivative? So when we're below 0, let's just take a point. Let's say h prime of negative 1. H prime of negative 1 is equal to what? That is equal to negative 1 to the third is negative 1 minus 2 times negative 1 squared. Well, negative 1 squared is just positive 1, right? So it's minus 2, right? So it equals minus 3. Okay, let's take a point in between these two. Well, 1 is in between them, so let's just take h prime of 1 is equal to 1 minus 2. 1 minus, let's make sure I'm doing that right. 1 minus 2, right? Because it's 1 squared. So it equals negative 1. H prime of 1. And then what happens when we go of z values greater than 2? So let's try 3. H prime of 3 is equal to what? H prime of 3 is equal to 27. What's minus 2 times 9? It's equal to 9, right? 18, right? H right. So it's positive. So what do we know? We know that, and in all fairness, this is kind of an interesting problem, because the derivative is negative. So if we were to draw the derivative of this, what are the interesting points? It's 0. So that's the x-axis. That's 0, and then we had 2. And this, I'm going to draw the derivative. I'm not drawing the actual function. Because the monotonicity theorem, we care about when the derivative is positive or negative. So what this tells us is that the derivative, it was negative when we were to the left of 0, right? Because we just took a test point, because we know it's 0 here. But then what happened? It's not like it got positive then. It went back negative again when we tried the derivative at 1. So it probably does something like this. It probably does something like this. And then, now what would it be? Let's see. And then it goes up at 2 where it's greater than 0. Right. I was confusing myself for a second. Right. So the derivative, it probably, right, it starts, but it never goes above right there. So the derivative probably has a bit of a, it probably has a bit of a maximum point there or something. This is the derivative, remember. That's how I was confusing myself. And then it probably flips around and then goes above there. But from the monotonicity theorem, what do we care about? We care about the intervals where the derivative is positive and the derivative is negative. So the derivative is positive for all of these values, for z is greater than 2, right? So we could say, using the monotonicity theorem, this function is increasing when z is greater than 2. So let me write that. Increasing when z is greater than 2. And then we can say that the function is decreasing. Function, we could say flat or decreasing, right? Because the slope of the function is 0 right here. And remember, this is the graph of the derivative. So we could say flat or decreasing when z is less than 2. And depending, you normally do consider flat monotonic kind of in one direction. So you could say monotonic increasing would still include something that kind of flattens out. Well, anyway, I'm pushing 10 minutes, and I don't think I have time for the next problem, which I might do in the next video, but hopefully you found that a little bit helpful and not too confusing. I will see you in the next video.